my name is Dawn Matthews. Welcome to this lesson in the series on data representation in computers. In the first lesson, we learned that the language that a computer understands is composed entirely of zeros and ones. We say that the zeros and ones are binary data. In the second lesson, we saw that characters are represented by binary codes, but that numbers use the binary numbering system. By the end of this lesson, you should be able to convert numbers from the decimal system to the binary system, convert numbers from the binary system to the decimal system. Do you remember how many bits make a byte?
Well, that's easy. 8.
Correct. And how many bytes are needed to represent one character in ASCII code?
1 byte.
Well done. If we have the binary number 10011 base 2, how would we find out its decimal value? In other words, how do we convert a binary number to a decimal number that we can understand more easily? I've left you a worksheet to do. See how far you can go on your own.
1. Do you remember how to find the decimal equivalent of a binary number?
I don't really remember, but she gave us a hint here and it says, write the number in expanded notation and then complete the sum. If I remember correctly, we write out the number as a sum of the powers of 2.
That's right. We start counting the positions of the digits from the right-hand side, starting with 0. So it's 0, 1, 2, 3, 4. Then we write down each digit multiplied by 2 to the power of the position. So the first digit has a value of 1 times 2 to the power of 0.
And then the next is 1. And what we do is that we say 1 times 2 to the power of 1, then we get 0 times 2 to the power of 2. Then we get 0 again, and now we're in the third position. So it's going to be 0 times 2 to the power of 3. Now the last digit we have is going to be 1. So it's going to be 1 times 2 to the power of 4.
Working that out, we get 1 times 2 to the power 0, which is 1. In maths, you would have learned that anything to the power 0 is equal to 1. Plus, 1 times 2 to the power 1 is just 2. Plus, 0 times 2 squared, which is 4. Plus 0 times 2 the power of 3, which is 8 plus 1 times 2 to the power 4, which is 16. That then gives us 1 times 1, which is 1, plus 1 times 2, which is 2, plus 0. 0 times anything is 0, plus 0, plus 1 times 16, which is 16. Adding that all up, we get 1 plus 2, which is 3, plus 16, which gives us 19. We should then add the subscript 10 to show that this is base 10.
Cool, well, let's try task 2.
Yeah, it says convert the binary number 1010 to the base of 2 to its decimal equivalent.
Well, let's go through it together. First, count the number of digits from the right, starting at 0. 0, 1, 2, 3. Then it's 0 times 2 to the power 0, plus 1 times 2 to the power 1, plus 0 times 2 to the power 2, plus 1 times 2 to the power 3. That gives us 0 plus 2 plus 0 plus 8, which is equal to 10. Remember to write the subscript. Now you know how to convert a binary number to a decimal number.
Dawn, I got 49 out of 50 for my multiple choice test. Now I know that our teacher keeps our marks on a computer. Now how would my mark be represented in binary?
What you're asking now, Archie, is how do we convert a decimal number to a binary number?
Remember our table from lesson 2.
We discovered a pattern, n is equal to 2 to the power of n. That described the number of combinations that were possible for a certain number of bits. When a user enters a decimal number, the computer has to convert to binary using this pattern. It does this by subtracting the highest number of combinations from the decimal number and then following the same process with the remainder. Take the test mark 49, for example. Hey. Think about the highest number of combination of bits that would fit into 49. Then use the remainder and follow the same process. For example, 49 is equal to 32 plus 16 plus 1. That is 2 to the power of 5 plus 2 to the power of 4 plus 2 to the power of 0.
Now looking at the answer, we can write a 1 wherever we had a result and a 0 where we did not have a result. And 49 is equal to 1100001 to the base of 2.
The method we use here is to divide repeatedly by 2 and keep track of the remainders.
You mean another conversion from decimal to binary?
Okay guys, this is how we work it out. We start with your mark 49. 49 divided by 2 is 24, remainder 1. We then divide 24 by 2. We ignore the previous remainder. 24 divided by 2 is 12, remainder 0. 12 divided by 2 is equal 6, remainder 0. 6 divided by 2 is equal 3, remainder 0. 3 divided by 2 is equal 1, remainder 1. 1 divided by 2 is equal 0, remainder 1. We must carry on until we get 0. The last answer will always give you 0, remainder 1. So now we write down the remainders from the last to the first, left to right. That gives us 1, 1, 0, 0, 0, 1 base 2. And that's the answer. 49 base 10 equals 1, 1, 0, 0, 0, 1 base 2. Archie, you look very doubtful. Why don't you convert it back to decimal to check?
Okay, let's try this. And that's going to give us 1 times 2 to the power of 0.
Yes.
Plus 0 times 2 to the power of 1. 0 times 2 to the power of 2. Then plus 0 times 2 to the power of 3. Then here we're going to say plus 1 times 2 to the power of 4 plus 1 times 2 to the power of 5. That's going to give us 1 plus 0 plus 0 plus 0 plus 16 plus 32, and that is going to give us 49.
Yes, Archie, working with the binary system is really not too difficult. How about converting 27 base 10 to binary?
Remainder 1. Okay, so we say 13 divided by 2. This will give us 6. Remainder 1. 6 divided by 2. This will give us 3. No remainder. Remainder 0. And then 3 divided by 2. This will give us 1. Remainder 1. And then 2 divided by 2. This will give us 1.
1.
It's going to remainder 0. Then 1 divided by 2 will give us 0, remainder 1. So we get 1, 1, 0, 1, 1. Okay, I get 1, 1, 0, 1, 1 to the base of 2.
Well done. It looks like you really understand this binary number system. Let's look at the difference between characters and numbers again. If, for example, we want to store your address, which is 27 Ring Road, we would want to store the number 27 and the rest of the address as characters in the computers, not as numbers. We would use the ASCII character values for each digit or letter, like this. But let's say 27 is your mark for a test out of 30, and we want to work out what your percentage for the test is. That means we want to do arithmetic with the 27. We want to divide 27 by 30 and multiply the answer by 100. Then we should rather store 27 as a number. If the computer has a 16-bit word size, it would look like this. We know that 27 base 10 is 11011 base 2. That's only 5 bits. So then we must fill up with zeros to the left until we have 16 bits. You can see that 27 as a number and 27 as 2 ASCII characters look quite different. Everything you type in a word processor, whether it be numbers or letters of the alphabet, is stored as characters, also known as text. However, when you work with spreadsheets, databases and programming, you need to decide in what format you're going to store the data. You must decide whether the number you want to store should be stored as characters or as a true binary number. Decide this by asking yourself whether or not you want to do arithmetic with a number. Let's take a telephone number. Would you want to add this to some other number? Use it in division? No? Then store it as characters. What about the amount you pay towards your school fees? I guess you would want to subtract that from the amount you owe. You do want to do arithmetic with it, therefore store it as a number. So Salai, you have learned many concepts today. Why don't you summarize for the viewers at home?
Well, I now understand that characters are stored in a computer as binary codes using, for example, ASCII codes, and that numbers are stored as binary values using the binary number system.
And we are also able to convert decimal to binary and binary back to decimal.
Good work, you guys. Here's your task for today. What is the word size of the computer you use? Convert the following binary numbers to decimal. 10110 base 2, 110011 base 2. Convert the following decimal numbers to binary. 38 base 10, 127 base 10. Represent the number 17, such as in 17 Learn Street, as characters in binary using ASCII codes. Represent the number 17, such as a mark of 17 out of 30, as a number in the binary number system. Be sure to join us again in the next lesson on data representation, when we will discuss another number system, hexadecimal. And as always, don't forget to go to our website for more information. From me, goodbye.